I am so glad you're joining me today because we are going to unpack something truly fascinating. We're looking at a brand new paper from Meta AI that introduces a model called Tuna-2. Now, we all know the world of artificial intelligence moves at absolutely breakneck speed, but today we're actually going to slow down a bit. We're going to take our time and really unpack the complex architecture behind Tuna-2. Because by the end of this explainer, you're going to understand exactly why this paper represents a massive paradigm shift for the entire AI industry.
Okay, let's dive into this. Here's our roadmap for today. First, the AI multimodal problem. Second, defining the tech jargon. Third, introducing Tuna-2. Fourth, Pixel's over vision encoders. And finally, why this matters right now.
So, starting with Section 1, the AI multimodal problem. To really get why Tuna-2 is such a huge deal, we first need to understand the holy grail of current AI research. Right now, everybody wants a unified multimodal model. That means an AI that can see an image, understand it, and also generate an image, all in one seamless system. But currently, the architectures we use to do this are facing a massive misalignment between understanding and generation. Let's just take a second to think about that. Right now, unified multimodal models use entirely separate visual representations for understanding an image versus creating one. It's kind of like having two completely different brains trying to do one job. Because the AI uses one mechanism to comprehend what it's seeing and a completely different one to draw it, there's just a fundamental disconnect. They are totally misaligned.
And this misalignment, it creates what we call traditional bottlenecks. These are really holding us back. You see, we rely heavily on pre-trained vision encoders, which are what create those separate visual representations we just talked about. And crucially, having these completely prevents the model from achieving a fully end-to-end optimization directly from the raw pixels. Basically, current models rely on clumsy middlemen systems, rather than just working directly with the core data right in front of them.
That brings us to Section 2, defining the tech target.
I know this gets technical fast, so let's deliberately walk through these terms. First up, the pre-trained vision encoder. What is it? Well, it's that modular middleman system, like a VAE, or variational autoencoder, that traditional AI models use to translate visual input. Imagine you're trying to read a book in a language you don't speak, right? So you hire a translator. The translator reads the book, summarizes it, and then tells you what it means. That translator is the vision encoder. It's an extra, completely separate step that just slows down your actual direct understanding of the source material.
Now, on the flip side, we have Pixel Embeddings. This is a method of processing data directly from the raw pixels of an image, completely bypassing the need for a modular middleman. If the vision encoder was like relying on a translator, Pixel Embeddings are like being a native speaker. You are looking directly at the source, the raw pixels, and understanding them natively, instantly, without anyone getting in the way to interpret them for you.
And this brilliantly sets us up for Section 3, introducing Tuna-2. Tuna-2 is Meta AI's incredibly elegant solution to those bloated middleman bottlenecks we just went over. And I do want to briefly credit the team behind this massive breakthrough. Tuna-2 was developed by a team of Meta AI researchers, including Zhihong Liu, Weiming Ren, Yurin Kong, and several others. They submitted this paper to the Hugging Face community on April 28th, and man, it immediately caught the attention of the AI world because of how cleanly it solves the multimodal problem.
Right in their abstract, the researchers state that Tuna-2 drastically simplifies the model architecture by employing simple patch embedding layers. I really want to emphasize those two words, drastically simplifies. You know, in an industry where models are just constantly getting larger, more complex, and honestly more tangled, Tuna-2 goes in the exact opposite direction. It strips away all that bloated architecture of the past.
When you starkly contrast these two methods, the difference is wild. The old way relies on modular vision encoders and VAEs. It's this latent space approach that is just chunky and divided. But the new way, the Tuna-2 way, is a native, unified model using raw pixel embeddings. It is a complete structural departure. It's literally taking that translator out of the room entirely and teaching the AI to natively read the pixels.
So how exactly does Tuna-2 pull this off? It actually comes down to two surprisingly digestible steps. Step 1, completely discard modular vision encoder designs. Just throw them out. Gone. Step 2, use simple patch embedding layers to directly encode the visual input. And that's it. No separate representations for understanding versus generation. By processing the visual data directly from the pixel embeddings, Tuna-2 creates a truly native end-to-end multimodal model. Just let the simplicity of that engineering solution sink in for a second.
Let's move to Section 4, Pixels over vision encoders. Okay, so it's one thing to have a simpler, more elegant theory, but it's another thing entirely to prove it actually works in practice, right? Well, the benchmark results speak for themselves. First off, Tuna-2 achieves state-of-the-art performance in multimodal benchmarks. Second, it demonstrates that unified pixel space modeling can compete fully with those old latent space approaches when we're talking about high-quality image generation. And third, it achieves much stronger multimodal understanding at scale. So simplifying the model didn't just maintain the status quo, it literally led to better state-of-the-art results.
Now, what's really interesting here is that there is one notable trade-off the researchers found. During early pre-training, the old encoder-based variants actually converge faster. They kind of get off the starting line a bit quicker. But at scale, Tuna-2's encoder-free design wins out significantly. Once you scale the model up, that native understanding of the pixels allows Tuna-2 to achieve a much stronger overall understanding than any of the models relying on middleman encoders.
And this leads to a very specific, absolutely critical strength. Tuna-2 excels particularly on tasks requiring fine-grained visual perception. And think about why that makes perfect sense based on what we've learned today. If an AI relies on a summary from a translator, it's probably going to miss the tiny nuances of the original text. But because Tuna-2 uses direct pixel space modeling, it is looking directly at the raw image data. It makes the AI so much better at noticing those tiny, intricate, fine-grained details.
Which brings us to our final section, why this matters now.
We've gone through the technical architecture, but I really want to prepare you for the overarching philosophical shift this paper represents for the whole AI industry moving forward. Here are the massive takeaways. Number one, and this is a huge statement, pre-trained vision encoders are simply not necessary for multimodal modeling. The old crutch can just be thrown away. Number two, end-to-end pixel space learning is the future. It is just a cleaner, natively unified way to build an AI. And number three, this offers a highly scalable path toward much stronger visual representations for both generation and perception.
I want to leave you pondering this provocative thought. If pre-trained vision encoders, something the industry basically considered standard practice, aren't actually necessary, what other complex AI rules are ready to be broken? Tuna-2 proves that sometimes the greatest breakthroughs don't come from adding more complexity, but from finding the courage to drastically simplify. Thank you so much for taking the time to slowly walk through this fascinating paper with me today on The Explainer. Keep questioning the standard models, keep exploring, and I will see you next time.